A comet just erupted near the sun, and now a massive solar storm is racing to meet it on a collision course. In the next few weeks, Comet C/2025 R2 Swan will make its closest approach to Earth in recorded history, just as the sun unleashes its mightiest flare in months. This cosmic alignment is incredibly rare. We have a volatile comet, a powerful solar eruption, and a front-row seat from Earth. What happens when a solar storm meets a cosmic visitor? Let's explore this extraordinary scenario together.
First light, the outburst begins.
Comets are notoriously unpredictable, but what happened on September 26 caught everyone by surprise. Just 2 weeks after its closest pass to the Sun at a perihelion of 0.5 astronomical units, Comet Swan suddenly roared to life. Initially, it was a faint object, but amateur astronomers in Japan and Australia noticed a dramatic surge in brightness overnight. This wasn't a minor flicker. The comet's brightness leaped by a full magnitude, from 7.4 to a peak of 5.7, pushing it into naked-eye visibility under dark skies. What caused this? As the comet swung away from the sun, intense solar heat penetrated its frozen nucleus. Pockets of sublimating cryovolatiles like frozen carbon monoxide and carbon dioxide buried for millennia reached their breaking point and exploded through the crust. This outburst ejected a massive cloud of gas and dust, dramatically expanding the comet's atmosphere, or coma, and feeding its enormous tail. According to cometary scientist Dr. Casey Liss of the Johns Hopkins Applied Physics Laboratory, such outbursts provide a rare glimpse into the primordial material from which our solar system was formed. This event signaled that Swan's inner engine was now exposed, making its next moves completely unpredictable, and turning it into a prime target for skywatchers worldwide. The sudden release of energy was so significant it altered the comet's light curve, deviating sharply from all predictive models.
Anatomy of a tail.
This isn't just a faint smudge in the sky. We're talking about a structure wider than 5 full moons laid end to end, stretching over 15 million kilometers through space. And its design tells a story. Comets actually have 2 distinct tails, and Swan's outburst put both on magnificent display. The first is the dust tail. It's broad, curved, and shines a pale yellow as it reflects sunlight. It's made of heavier micron-sized particles that are pushed gently by solar radiation pressure and tend to lag behind in the comet's orbit. The second, and more dramatic, is the ion tail. This tail is a narrow, straight ribbon of electric blue, composed of ionized gas like carbon monoxide ions, or CO+, which fluoresce brightly when excited by solar ultraviolet radiation. This glowing stream is blown directly away from the sun by the solar wind at speeds exceeding 400 kilometers per second, acting like a cosmic windsock. As noted by comet expert Carl Battams of the U.S. Naval Research Laboratory, the ion tail is a perfect natural probe of interplanetary conditions. With Swan's tail now stretching across a huge patch of sky, it has become a perfect natural laboratory, exquisitely sensitive to the solar storm that is now heading its way.
The sun awakens.
Just as the comet was putting on its show, the sun, which had been quiet for weeks, decided to join the party with its most powerful eruption in months. On September 28, at 0843 Universal Time, satellites from the GOES network detected a massive spike in X-ray emissions, jumping from a background level of 10 to the -6 to 6.4 times 10 to the -5 watts per square meter. An M6.4 class solar flare had erupted from a magnetically complex sunspot group designated Active Region 4232, then rotating into view on the sun's southeastern limb. M-class flares are the second strongest category, and a 6.4 is a significant event powerful enough to cause radio blackouts on the sunlit side of Earth. Scientists at NOAA's Space Weather Prediction Center, like lead forecaster Dr. Alexei Pevtsov, immediately began analyzing data from the Solar Dynamics Observatory's AIA instrument at multiple wavelengths, including 131 angstroms, to assess the flare's power and, more importantly, what it threw into space. The energy release was equivalent to millions of hydrogen bombs detonating simultaneously. The timing was incredible. Just 2 days after the comet's own eruption, the sun had fired a warning shot into the exact same quadrant of space.
Plasma on the move.
A flare is just the flash of light. The real power is in the billion-ton cloud of magnetized plasma it can hurl into space. And, this one wasn't aimed at us. Within minutes of the flare, coronagraphs aboard the SOHO spacecraft, specifically the LASCO C2 and C3 instruments, confirmed that a massive coronal mass ejection, or CME, had been launched. This wasn't just a puff of smoke. It was a colossal bubble of solar material and magnetic fields, with an estimated mass of 1 trillion kilograms, racing outwards at a staggering speed between 800 and 1,000 kilometers per second. Forecasters at NOAA's Space Weather Prediction Center, using the WSA Enlil prediction model, quickly charted its trajectory. The verdict: Earth was in the clear. But the CME was barreling directly towards the region of space now occupied by Comet Swan and its magnificent sprawling tail. Solar physicist Dr. Angelos Vorlidas, a leading expert in CME imaging, confirmed the CME's broad 90-degree angular width made an encounter highly probable. A rare and potentially violent collision was now inevitable within 48 to 72 hours.
Magnetic scissors.
So, what happens when a comet's tail, which is a magnetic structure, meets a massive magnetic cloud from the sun? Sometimes things just snap. This phenomenon is called magnetic reconnection, and it's one of the most explosive processes in the solar system. A comet's ion tail is made of plasma, held together by magnetic field lines streaming away from the sun. A CME, however, is a tangled web of powerful magnetic fields, often containing a strong southward-pointing component, known as the Bez field. If this southward Bez field, with a strength potentially exceeding 20 nanoteslas, slams into the comet's oppositely directed magnetic field, they can't merge. Instead, they collide, break apart, and explosively reconnect into a new shape. As space plasma physicist Dr. James Drake has explained, this process converts magnetic energy into kinetic energy with incredible efficiency. When this happens, the energy release can be immense, acting like a pair of magnetic scissors that cleanly severs the entire ion tail from the comet's head. This is called a disconnection event, and it can happen in a matter of minutes, leaving the old tail to drift away as a new one begins to form.
The forecaster's puzzle.
Predicting this collision is more complex than it sounds. It's like trying to predict if one puff of smoke will hit another in a hurricane. While models from NOAA's Space Weather Prediction Center, like the Enlil heliospheric model, showed the CME's main lobe sweeping through Swan's sector, CMEs expand, twist, and deform as they travel hundreds of millions of kilometers through space. Hitting a relatively small target like a comet's tail is not a guarantee. The biggest challenge for forecasters is the lack of direct measurements. Since the CME is not aimed at Earth, we won't get in-situ data from satellites like the DSCOVR spacecraft, which normally act as a warning system by sampling the solar wind a million miles upstream from us. Scientists must rely on images from spacecraft like SOHO and Stereo A to refine the CME's trajectory and predict the exact time of impact. An error of just a few degrees in the initial launch angle can result in a 10 million kilometer miss by the time it reaches the comet. The best estimates place the arrival between 48 and 72 hours after the flare. But the question remains, will it be a direct hit, a glancing blow, or a near miss?
Citizen science mobilizes.
When a cosmic event like this unfolds, the big observatories aren't the only ones watching. A global network of backyard astronomers becomes the front line. Professional telescopes have schedules booked months in advance, so they can't always drop everything to watch a single event. Citizen scientists, however, can provide continuous, round-the-clock coverage. This is crucial because a tail disconnection event can be incredibly fast, unfolding in less than 2 hours. An amateur astronomer with a modest setup, like a 10-inch reflector and a modern CCD camera, could be the first person to capture the collision. Organizations like the Association of Lunar and Planetary Observers, or ALPO, have entire sections dedicated to coordinating comet observations. Renowned astrophotographer Damian Peach has shown how high-resolution amateur images can rival those from professional instruments. These observers are not just taking pretty pictures. They are collecting valuable scientific data, or photometry, that can be used to measure brightness changes and map the tail's structure with incredible detail, helping to build a global record of this rare encounter.
The perfect alignment.
As if a volatile comet and a perfectly aimed solar storm weren't enough, the celestial geometry for this event is almost unbelievable. On October 21, 2025, Comet Swan will make its closest approach to Earth, passing just 0.25 astronomical units, or 39 million kilometers away. That's roughly 100 times the distance to the Moon. For a comet with an orbital eccentricity of 0.98 and a low inclination, that's an exceptionally close flyby. This proximity makes it an easier target for even small telescopes. The timing is equally perfect, coinciding with a new moon, meaning the sky will be at its darkest. But there's more. On that same date, a hypothetical interstellar visitor, 3I Atlas, reaches a superior conjunction on the other side of the Sun. As orbital dynamicist Dr. Davide Farnocchia from NASA's Jet Propulsion Laboratory would note, the probability of a dynamically new comet like Swan and an interstellar object aligning so closely in time and space is vanishingly small. This alignment provides a unique chance to compare a native solar system body with an interstellar one under the same solar conditions, a rare convergence of a dynamic comet, a potent solar storm, and an ideal observation window from Earth.
Southern skies, spotlight.
For these crucial weeks, the best seats for this cosmic show are in the Southern Hemisphere. From major observatories like the Siding Spring Observatory in Australia to backyard setups in South Africa and South America, Comet Swan will be high in the sky after sunset. Its path takes it through the southern constellations of Grus and Piscis Austrinus, passing near the bright guide star Fomalhaut. Viewers can use this star as a guidepost to locate the comet, which will appear as a fuzzy star with a long, faint streak extending from it. Even a standard pair of 7x50 binoculars will be enough to reveal the tail, stretching over 2.5 degrees, the width of 5 full moons. For those in the northern hemisphere, the view will improve throughout October as the comet climbs higher in the western sky after midnight. The checklist for observers is simple. Find a dark sky, use a star chart to locate the comet, and watch for any changes. By taking images every few minutes, observers can create time lapses that will reveal the tail's motion and any sudden disruptions caused by the solar wind in stunning detail.
Cosmic forces collide.
Here's the bottom line. We have a comet that has just undergone a massive outburst, making it unusually active and producing a large, dense tail. We have a powerful M6.4 flare that launched a CME racing directly towards it at nearly 1,000 kilometers per second. And we have a historically close and well-timed approach to Earth, giving us a perfect view. This sets up a documented encounter between a solar storm and a comet's ion tail, a phenomenon that could cause dramatic changes, with spectral analysis potentially showing Doppler shifts in ion velocities of up to 50 kilometers per second. It's important to be clear, as a scientist from a program like the NASA Comet Observation Database would emphasize, the comet's initial outburst and the solar flare are a coincidence. The sun did not cause the comet to erupt. However, this coincidence has created a rare opportunity for both professional and amateur observers to witness the powerful dynamics of our solar system in real time. The key results are still unfolding, written in gas and light across the night sky. A cosmic experiment for the entire world to watch. We are witnessing a truly unique cosmic alignment, a volatile comet, a powerful solar storm, and a front-row seat from Earth. What will happen when the CME slams into Swan's tail is still unknown. Will it be a gentle ripple or a dramatic disconnection that severs the tail completely? The only way to find out is to look up. This is a rare opportunity for anyone with a pair of binoculars or a small telescope to contribute to a global science campaign. The universe is putting on a show, reminding us of the immense and unpredictable forces at play. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Sci and Why.
What if the third interstellar visitor ever discovered was not a comet, but a billion-year-old alien messenger? In the summer of 2025, a faint object designated 3I Atlas streaked into our solar system, and a controversial hypothesis immediately captured the world's attention. This was no ordinary rock. The idea of advanced alien technology made global headlines, but NASA quickly stepped in with a powerful, evidence-based response that settled the debate. So what did they find? Let's explore this together. The Atlas discovery in Chile. So, where does a story like this begin? It starts with our ever-watchful eyes on the sky. The story began on July 1, 2025, when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic survey telescope at the El Sos Observatory in Chile, detected a faint object with an initial apparent magnitude of plus 19.5. To put that in perspective, that's about 250,000 times fainter than what the human eye can see. When astronomers calculated its orbit, they saw something remarkable. Its path was hyperbolic with an orbital eccentricity calculated to be a staggering 1.8. In astronomy, any orbit with an eccentricity greater than 1 is unbound. This number confirmed it was moving at approximately 55 kilometers per second relative to the Sun, far too fast to be a member of our solar system. Astronomers quickly named it 3I Atlas. Initial estimates suggested it could be massive, between a few hundred meters and several kilometers across, making it potentially much larger than the previous 2 interstellar visitors. The discovery was a major success for the Atlas network, which also includes telescopes in Hawaii and South Africa, proving its effectiveness in spotting these rare cosmic travelers. The detection of a third such object in less than a decade confirmed that these visitors are more common than previously thought, officially opening a new frontier in astronomy. Avi Loeb's controversial hypothesis. Here's where the story takes a sharp turn into speculative territory, thanks to a bold proposal from Harvard astronomer Avi Loeb. While most scientists saw a fascinating natural object, Loeb, known for his controversial work on Oumuamua, offered a different interpretation. In a scientific paper posted to the ArcSiv preprint server, Loeb pointed to the object's early lack of a visible coma and its trajectory. He suggested that if the comet continued to show no outgassing, or if its path deviated from a purely gravitational path without a visible tail to explain the push, it could be evidence of something artificial. He even raised the hypothetical possibility of malign intent, though he stressed this was an intellectual exercise meant to keep science open to radical possibilities. His argument, similar to the one he made for Oumuamua, hinged on the idea that any non-gravitational acceleration without a visible coma required a novel explanation. He proposed that a solar sail, a thin, lightweight craft pushed by the pressure of sunlight itself, was one such possibility that science should not be afraid to consider, however unlikely it might seem at first. The physics of radiation pressure are well understood, but for it to be effective, an object must have a huge surface area and an extremely low mass, characteristics not found in natural bodies. Media sensation versus scientific method. You can imagine what happened next. The words alien technology from a prominent Harvard astronomer ignited a media firestorm. The idea was captivating, offering a sensational explanation for a new cosmic puzzle. But this is where the rapid world of headlines collides with the methodical, patient pace of science. The scientific method isn't about finding the most exciting answer, it's about finding the one that best fits all the evidence. The broader astronomical community, while not dismissing Loeb's right to speculate, emphasized the need for patience and adherence to Occam's razor, the principle that the simplest explanation is often the best. Their stance was clear: we must first rule out all known natural phenomena before jumping to an extraordinary conclusion. The use of preprint servers like ArcSiv allows for rapid dissemination of ideas, but also bypasses the traditional peer review process, meaning speculative ideas can reach the public before they are fully vetted by other experts. Ultimately, the scientific consensus held that declaring an object alien required the elimination of every single possible natural explanation first, a very high bar that had not yet been met. NASA's comprehensive investigation. With the debate raging, NASA and its international partners marshaled their most powerful instruments. This wasn't a casual glance, it was a coordinated multi-platform investigation led by Tom Statler, NASA's lead scientist for small bodies. The agency dedicated priority time on the James Webb Space Telescope, using its near-infrared spectrograph, NIRSpec, to perform detailed chemical analysis of the gases in its coma. Simultaneously, the Hubble Space Telescope's Wide Field Camera 3 was used for high-resolution imaging to search for any faint dust or fragmentation events, thanks to its superior resolving power in visible and ultraviolet light. On the ground, a network of observatories, including the twin 10-meter mirrors of the Keck Observatory in Hawaii, began a long-term monitoring campaign to track its brightness and trajectory with pinpoint accuracy. The goal was to leave, honestly, no stone unturned, to precisely measure its path to within a few milliarc seconds, to analyze its chemical composition, and to study its light curve for clues about its shape and rotation. This multi-wavelength, multi-observatory approach is the gold standard in modern astronomy for characterizing a novel object. Comet behavior confirmed. So what did this powerful array of telescopes actually see? The answer was unambiguous, and came sooner than many expected. As 3I Atlas drew closer to the Sun, crossing the orbital distance of Jupiter at approximately 5.2 astronomical units, which is about 483 million miles, the solar radiation began to warm its icy surface. Just as predicted by standard cometary models, it started to sublimate, behaving exactly like a comet. Astronomers watched as it developed a distinct coma, the fuzzy, gaseous atmosphere around its nucleus, which grew to over 50,000 kilometers in diameter. Shortly after, a classic tale of gas and dust began to form. Tom Statler summarized the findings. It looks like a comet, it does comet things, and the evidence overwhelmingly points to it being a comet. The observation of outgassing with a dust production rate estimated at over 50 kilograms per second provided the natural explanation for any minor deviations in its path, rendering the artificiality hypothesis unnecessary. This behavior began right around the frost line where water ice turns to gas, a telltale sign of a natural cometary body. Chemical composition analysis. But confirming it was a comet was just the beginning. The real prize was in its chemistry. A team led by Dr. Anjali Sharma, a planetary scientist at NASA's Goddard Space Flight Center, used the James Webb Space Telescope's spectrographs to break down the faint light from the coma into its chemical fingerprints. The analysis revealed familiar substances like water ice and carbon dioxide, but with a major surprise, 3I Atlas had an unusually high ratio of carbon dioxide to water, measured at nearly 35%. This vital clue suggested the comet must have formed in an extremely cold region of its home star system, far out in its protoplanetary disk, where carbon dioxide could freeze out in large quantities. Furthermore, analysis of the dust grains showed a polarization signature with negative branching at a phase angle of 22 degrees, suggesting a surface composed of very fine, porous, fluffy dust grains, which is a sign of a very pristine, unaltered body. This fluffiness implies the grains have not been heavily processed by heat or collisions, making them a near-perfect sample of their native environment. This chemical snapshot provides invaluable data for models of planetary formation in other star systems. Trajectory and safety assessment. With the "what is it" question settled, NASA also moved to definitively address any public concern about its path. The coordinated tracking campaign from both space and ground-based telescopes allowed for an extremely precise calculation of its orbit. The agency confirmed that 3I Atlas posed absolutely no threat to Earth. Its closest approach to our planet will be a very safe 1.8 astronomical units, which is about 273 million kilometers or 170 million miles away. Its perihelion, or closest approach to the Sun, is predicted for January 12, 2026, at a distance of 1.5 AU, placing it between the orbits of Earth and Mars. NASA's Planetary Defense Coordination Office used this as a perfect real-world test of their tracking systems, proving they can accurately predict the path of even novel interstellar objects with incredible precision. After it loops around the Sun, its hyperbolic trajectory will ensure it is flung back out into interstellar space, never to return. Its brief passage is a fleeting but precious scientific opportunity. Natural anomalies in cometary physics. The whole 3I Atlas controversy really boils down to a single fundamental question in science. Is an anomaly evidence of something artificial, or is it a sign of a natural process we haven't encountered before? Science almost always bets on the latter. Our own solar system is filled with comets that behave in bizarre ways. Take Comet 29P Schwassmann-Wachmann, which can increase in brightness by over 15 magnitudes, a factor of 1 million, in just a few hours due to cryovolcanic eruptions. Another example was Comet C 2019 Y4 or Atlas, a different comet which unexpectedly disintegrated into multiple pieces as it approached the Sun, showing how fragile these icy bodies can be. The point NASA scientists made is that unusual traits are not automatic evidence of engineering. They are part of the normal, messy, and fascinating physics of icy bodies. These anomalies are not problems for science, they are the very data points that lead to new discoveries about how objects form and evolve. Thus, the unique chemistry of 3I Atlas isn't a paradox, it's a clue. Scientific value of interstellar visitors. So if 3I Atlas is not alien technology, why is it so important? Because interstellar comets are windows into other worlds. Each one is a preserved time capsule, carrying the precise chemical and physical fingerprints of the environment where it formed. For 3I Atlas, the dominance of carbon dioxide and its trajectory suggest it could be over 7 billion years old, originating from the Milky Way's thick disk, a population of ancient stars that existed long before our Sun was born. By studying its isotopic ratios like the deuterium to hydrogen ratio in its water, scientists can get direct clues about the water in other primordial solar systems, a key factor in assessing the potential for life elsewhere. This is more than a curiosity, it is a preserved fragment of another planetary nursery. Future missions, like the ESA's Comet Interceptor, are being designed specifically to launch and wait in space, ready to chase down the next interstellar visitor for an even closer look. These objects represent a fundamental shift from studying other solar systems through the faint light of their stars to analyzing actual, physical samples. Comparing 3 interstellar objects. To truly appreciate 3I Atlas, you have to place it in context with its predecessors. The first, Oumuamua, discovered in 2017 with an eccentricity of 1.2, was a complete enigma. It was small, rocky-looking, showed no visible coma, yet had a mysterious acceleration. The second, 2I Borisov, found in 2019 with a high eccentricity of 3.37, was almost the opposite. Its nucleus was about 1 kilometer wide and it behaved like a classic comet, allowing for detailed study. 3I Atlas, with its eccentricity of 1.8, falls between these extremes. It behaves like a comet, which sets it apart from Oumuamua, but its distinctive chemical ratios make it stand out from a standard comet like Borisov. This growing diversity is forcing astronomers to create a new classification system for interstellar objects. The current rate of discovery suggests that at any given time, there are likely thousands of interstellar objects within our solar system, but most are too small and faint to detect. As our technology improves, we can expect to find many more of these cosmic messengers, each one adding another piece to the vast puzzle of our galaxy. In the end, Comet 3I Atlas isn't alien technology. It's a natural interstellar comet. A stunningly beautiful and scientifically priceless messenger from another star system, shedding gas and dust as it speeds through our cosmic neighborhood. The real story here isn't science fiction, but the incredible power of science itself to solve mysteries and reveal the universe's secrets. It's a rare glimpse of pristine material from another world, reminding us that the cosmos is far more diverse and fascinating than we can imagine. For more deep dives into the mysteries of our universe, don't forget to like, subscribe, and hit the bell icon. The universe always has another surprise waiting. Thank you for watching Sci and Why. An object from another star system is blazing through our own, and it's putting on a show that has astronomers scrambling. This isn't just another rock, it's an interstellar messenger that's rewriting the rules as it gets closer to our sun, glowing 6 times brighter than anyone predicted. What is fueling this incredible outburst, and what secrets from a distant star does it carry? Let's explore this together. The numbers don't lie. So what do we actually know about this visitor? Let's break down the hard data. Right now, the interstellar comet designated 3I Atlas is roughly 2 astronomical units from the Sun. That's double the distance between the Earth and our star, about 300 million kilometers. Its speed is almost difficult to comprehend. It's currently traveling at nearly 60 kilometers per second and is still accelerating. By the time it makes its closest approach to the Sun, that velocity will peak near 68 kilometers per second. To put that in perspective, that's more than twice the speed of any planet, and fast enough to travel from the Earth to the Moon in a little over an hour. On the brightness scale, 3I Atlas has reached an apparent magnitude of 12. While that's about 250 times too faint for the naked eye, its brightness has been climbing far more rapidly than any models predicted. Its coma, the cloud of gas and dust surrounding the nucleus, has expanded explosively, now rivaling the diameter of Jupiter. While a typical comet nucleus is only a few kilometers across, this expanding atmosphere is what makes it so visible. The sheer scale of this coma is a key reason why it's appearing so much brighter than expected. The unexpected brightness surge. Why is this object causing such a stir? It all comes down to a sudden dramatic change. In September, 3I Atlas experienced a massive surge in brightness that defied all expectations. The light curve, which is the chart astronomers use to track an object's brightness over time, shot sharply upwards, veering completely off the predicted path. This wasn't a minor increase. The object is now glowing 6 times brighter than models had forecast, a jump of nearly 2 full magnitudes. This jolt sent a wave of excitement and debate through the astronomy community, with experts like Matthew Knight, a specialist in cometary outbursts, analyzing the data. The core of this mystery lies in its coma, the vast cloud of gas and dust that surrounds its nucleus. As the comet gets closer to the sun, its ices are vaporizing at an accelerated rate, causing the coma to swell to an enormous size, now spanning several 100,000 kilometers. This giant cloud is reflecting and scattering more sunlight back towards us, making the entire object appear far brighter in our telescopes. The rapid brightening suggests that highly volatile ices like frozen carbon monoxide or carbon dioxide, which vaporize farther from the sun than water ice, are driving the activity. Racing against the sun's glare. For astronomers on Earth, the clock is ticking. By early October, the window to observe 3I Atlas is closing, and fast. Every evening the comet appears lower in the twilight sky, getting progressively closer to the blinding glare of the sun. The angle between the comet and the sun, what astronomers call solar elongation, will shrink below 30 degrees by October 21st. That's the critical threshold where even the world's most powerful ground-based telescopes, like the Very Large Telescope in Chile, can no longer distinguish the comet's faint glow from the overwhelming brightness of the sky. Amateur astronomy networks are in a frenzy, trying to capture the last possible images before the blackout. Professional observatories, bound by strict safety protocols to protect their sensitive equipment, have already begun to scale back their observations. Pointing a multi-million-dollar telescope too close to the sun is a risk few are willing to take, as it can permanently damage the sensitive optics. This data blackout is happening just as the comet is expected to reach its most active and interesting phase, leaving a huge gap in our understanding. Mars, the last outpost. Just as Earth's view is about to be lost, the observational challenge shifts 225 million kilometers away to Mars. For a short but critical window, the red planet becomes the only outpost with a front-row seat. A fleet of robotic orbiters will become our eyes and ears. The European Space Agency's Mars Express can capture high-resolution images and chemical fingerprints of the coma. The ExoMars Trace Gas Orbiter is designed to sniff out faint traces of gases like water and carbon dioxide, giving us clues to its composition. NASA's MAVEN, led by principal investigator Bruce Jakosky, can use its ultraviolet spectrograph to study emissions from the comet's gas and dust, while the Mars Reconnaissance Orbiter could potentially resolve the nucleus itself with its powerful HiRISE camera, which can see features as small as 1 foot across from an altitude of 300 kilometers. On October 3rd, 3I Atlas will pass within 28 million kilometers of Mars, close enough for detailed study, but far enough to avoid any danger to the spacecraft. This encounter is our last, best chance to gather close-range data before the comet disappears from view. The Green Mystery. One of the most captivating features of 3I Atlas is its stunning green glow. What's causing this otherworldly color? Spectral analysis points directly to a molecule called diatomic carbon, or C2. Here's how it works. As the comet gets pummeled by solar radiation, the sunlight breaks apart larger carbon-rich parent molecules on the surface through a process called photodissociation. This process excites the resulting C2 molecules, and as they relax back to a lower energy state, they release photons of light specifically in the green part of the spectrum, primarily in what are known as the Swan bands around 510 nanometers. This phenomenon is seen in many comets, but the intensity of the green hue in 3I Atlas is exceptional. The work of Nobel laureate Gerhard Hertzberg, who pioneered the study of molecular spectroscopy, provides the foundation for understanding these emissions. This color is a real-time indicator of how rapidly the comet's surface is changing and shedding material as it barrels towards the sun. The impossible anti-tail. As if a green glow wasn't strange enough, some observers have reported something even more bizarre, a faint feature pointing towards the sun. This is a so-called anti-tail, and it appears to defy the laws of physics. We normally expect a comet's tail to be pushed away from the sun by solar wind and radiation pressure, a phenomenon seen in famous comets like Comet R2 Swan. However, the unique geometry of this encounter combined with the comet's incredible speed creates a different phenomenon. As 3I Atlas ejects larger dust grains, those particles are less affected by solar pressure and tend to remain in the comet's orbital plane. From Earth's perspective, as we cross that plane, some of this dust can appear to project towards the sun, creating a sunward spike. The late Michael A. Hearn, a leading expert in cometary dust, developed models to explain these complex dynamics, showing how electromagnetic forces can sometimes rival gravity's influence on charged dust particles. While reports of the anti-tail are still tentative, its presence would add another layer of intrigue to this already mysterious visitor. Not like the others. So, to truly understand just how unusual 3I Atlas is, we have to compare it to the only other interstellar visitors we've ever seen. The first, Oumuamua, discovered back in 2017, was a bizarre, cigar-shaped object with a high orbital eccentricity of 1.20 and, no visible coma or tail at all. It was basically a dry, inert shard just tumbling through our solar system. Then 2 years later, 2I Borisov arrived, and it looked way more like a classic comet, with an even higher eccentricity of 3.3. It had a bright coma, a well-defined dust tail, and a chemical makeup that was pretty similar to comets from our own Oort cloud. But 3I Atlas just refuses to fit into either of these boxes. Its coma is not only massive but also intensely green, which is a sign of strong diatomic carbon emission, something we just haven't seen with this kind of intensity in Borisov. And its dramatic brightness surge, a 6-fold increase above predictions, is unlike anything we've seen with the other two. According to University of Hawaii astronomer Karen Meach, this diversity really shows we have much to learn about the small body populations of other star systems. The Mars Encounter Strategy. The hopes of the entire astronomical community now rest on a handful of spacecraft orbiting Mars. Mission planners have spent weeks preparing for the October 3rd flyby, running simulations and allocating precious observation time. The goal is to get a multifaceted snapshot of the comet that would be impossible from Earth. Scientists want to use the high-resolution cameras like MRO's HiRISE, which has a 0.5-meter primary mirror, to try and spot the nucleus and measure its size and shape. Spectrometers will analyze the light from the coma to map the chemical composition of its gas and dust, telling us what kind of alien ices are vaporizing off its surface. Plasma instruments will study the interaction between the comet's atmosphere and the solar wind. No single spacecraft can do it all, and none have promised continuous coverage, but by combining data transmitted through the Deep Space Network, scientists hope to piece together a comprehensive profile of this interstellar visitor. It's a difficult observation, but the potential payoff is a groundbreaking understanding of a body from another star system. Chemistry in motion. Let's dive deeper into the chemistry that makes 3I Atlas so fascinating. The dominant green glow comes from diatomic carbon C2, but it's not the only molecule at play. Some early spectral readings have hinted at the presence of ionized carbon monoxide and the cyanogen radical, both of which can also contribute to a green or blue glow. Debates have already started in scientific forums about the precise mix of these chemicals, often relying on data from powerful spectrographs like the X-Shooter instrument on the VLT, which can cover wavelengths from the ultraviolet to the near-infrared in a single shot. The comet's incredible speed is a key factor here. It means that solar radiation is stripping away fresh, pristine ices from the nucleus at an astonishing rate. We are not just seeing ancient processed material from the surface. We are likely getting a look at the primordial parent molecules that were frozen inside this object when it formed billions of years ago in a completely different planetary system. This makes 3I Atlas a unique chemical laboratory. the fade begins. What happens after 3 I Atlas swings around the sun? Its brief moment of glory will be over and the fade will likely begin. Most models predict a sharp drop in brightness as the comet speeds away from the sun's heat, its vibrant coma shrinking and dispersing back into the void. For anyone hoping to catch a final glimpse, it will be a challenge. A large telescope with at least a 20-centimeter mirror will be the absolute minimum, and even then, it will likely appear as just a faint, fuzzy smudge. This is where citizen science will take over. Amateur astronomers and online networks similar to the American Association of Variable Star Observers will pool their observations, using techniques like image stacking to track the comet's retreat. These platforms provide real-time updates on its position and brightness, creating a light curve that professional astronomers will use to understand its behavior. The story doesn't end when it gets dim. Studying the post-perihelion light curve can reveal crucial details about the comet's structural integrity and whether it survived its fiery passage intact. The journey of 3 I Atlas through our solar system, though brief, leaves us with more questions than answers. Each data point gathered from this mysterious visitor helps us understand the diversity of objects that wander the galaxy. What does its unique composition tell us about the planetary system where it was born? How many more of these interstellar travelers are out there waiting to be discovered? As it slips back into the darkness, 3 I Atlas reminds us that our solar system is not an island, but part of a vast, interconnected cosmos. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. Thank you for watching Sci and Why.